In our previous lectures, we have derived numerical methods for numerical differentiation. We laid particular emphasis on the possible numerical instability that can arise in differentiation, and we have also laid emphasis on using a lower order formula, a first order or a second order formula, and then using Richardson extrapolation to improve the results. Very often, very dramatically, the results would improve by using the numerical differentiation of lower order and then applying the Richardson extrapolation. Let us now see how do we go about solving the problems of numerical integration. So, let us now take up numerical integration. What we are looking for is to write a formula for evaluating an integral of the form integral of a to b wx fx dx, where wx is a weight function, a positive quantity which is a weight function. Wherever the weight function is not required, we will take the integrand as a single quantity, as wx fx as a single quantity, but whenever we are require a weight function to use a particular integration formula, we shall then use that weight function for that purpose. Now, the interval a to b may be finite, it can be semi infinite or infinite. So, the interval a b can be finite interval, it can be semi infinite interval. So, that we have this as 0 to infinity, or it may be infinite. We shall consider all the three cases and derive numerical methods for obtaining this particular integral. The formulas usually are called the integration formulas or quadrature formulas. So, we can come across both the names by called integration formulas, or they are also called rules, or they are called quadrature rules. Now, what we would like to write is, since the integrand contains the unknown function fx, wx is a weight function which is known, the integral must be a linear combination of fx evaluated at a number of points between a and b. Therefore, I must be able to write this integral I, that is equal to integral a to b wx fx dx as a linear combination approximately as k is equal to 0 to n lambda k f of x k. Lambda k's are the parameters, and we are evaluating fx at a number of points in the interval a to b, and these points x k's are lying between in a b. Of course, we shall be using the end points also, wherever it is necessary we shall use the end points. For example, I can use x naught is equal to a, and I can use x n, the last point, as b also. However, we can construct formulas which do not use the values at the end points. Since we shall also call the x k's as abscissas of the quadrature rule. We shall call this as abscissas of the quadrature rule, and lambda k's shall be called as weights of the quadrature rule. So, these are weights and abscissas of a quadrature rule. Now, we can see that we are using in the integration formula a total number of n plus 1 abscissas. Since we are using n plus 1 abscissas, we shall call this as a n plus 1 point rule. So, we shall call this as a n plus 1 point rule. Now, as given in this formula, these x k's abscissas, there are n plus 1 that are there, there are n plus 1 weights also in this formula. If we take both of them as unknowns, that is abscess also to be determined, lambda case also to be determined, then there are a total of 2n plus 2 unknowns. This will be 2n plus 2 unknowns in the general case. Now, the error in the integration rule, we shall define it as we bring the right hand side to the left hand side and write down that as a error in the integration rule. So, I can define the error as some r n is equal to integral a to b w x f x dx minus summation k is equal to 0 to n lambda k f x k. Now, we need to define the order of a formula before we derive a formula, numerical integration formula. Let us define the order of a formula. So, let us say the order is p, let us say we call it as order p. Now, the method will be of order p if this rule integrates exactly polynomials of degree less than or equal to p. So, it must be able to integrate this exactly. So, if I use, if f x happens to be a polynomial of degree less than or equal to p, I substitute here, error would become 0, or it will exactly be, this will be an exact identity and I will have this is equal to this formula. If the rule integrates exactly polynomials of degree less than or equal to p, then order is equal to p. Now, when we say polynomials of degree less than or equal to p, it would imply that it is sufficient for us to consider 1 x, x squared, so on x to the power of p, because obviously if it is integrating these individually, a linear combination a naught plus a 1 x plus a 2 x square, it will automatically also it will integrate exactly. So, if you want to test whether it is integrating exactly or not, we just choose f x is equal to 1 x, x square, x to the power of p, substitute in this formula, then this would immediately give that error is 0. So, it is integrating exactly. So, this would also imply that R n is equal to 0 for f x, a polynomial of degree less than or equal to p. So, the error would be 0 if f x is a polynomial of degree less than or equal to p. So, this is how one can check whether the order is 1, 2 or 3 by just substituting it and then showing that the error is equal to 0 in these particular cases. Now, in the general case, we said that the formula has got 2n plus 2 unknowns, hence we can consider it as if it is a data given to us at 2n plus 2 points. Therefore, we can find a formula which will have the order 2n plus 1. So, therefore, if we have, since the number of unknowns in the general case is equal to 2n plus 2, therefore, the formula can be made exact to polynomials of degree less than or equal to 2n plus 1. That means, we are talking the order of the formula can be made as 2n plus 1. Sometimes the order is also called precision. So, we can also use the alternative name as a precision of the formula. Now, if we want to use the result that we know in the interpolation, particularly the Lagrange interpolation or the other interpolations, there the abscissas are all fixed. So, the data is given to us x k. So, x k is fixed. Therefore, if I want to use that formula, I need to fix my x k's. So, let us consider the case when when x k's are fixed. If x k are fixed, we have only lambda k's to be determined, therefore, these are n plus 1 unknowns. We have therefore only n plus 1 unknowns to be determined. Hence, we can make the formula exact polynomials degree less than or equal to n. Therefore, the formula can be made exact to polynomials of degree less than or equal to n. That means, order of the formula can be made as equal to n. Now, when once you say that x k's are fixed, then we can immediately say that we can use the Lagrange interpolation formula. Therefore, use Lagrange interpolation polynomial for f x. Therefore, we write integral a to b w x f x dx is equal to integral a to b w x into summation k is equal to 0 to n L k x f of x k plus pi x upon n plus 1 factorial f n plus 1 xi dx, where the abscissas x k's are given by a is equal to x naught less than x 1 less than x 2 and so on less than x n is equal to b. Now, let us simplify the right hand side. We write it as a sum of two integrals, integral of the first one and the integral of the second one. In the first integral, we can take the summation outside the integral sign. Also, f of x k is independent of x, therefore, we can take f x k also out of the integral sign. Therefore, we get integral a to b w x f x dx is equal to summation k is equal to 0 to n f of x k into integral a to b w x into L k x dx plus 1 upon n plus 1 factorial integral a to b w x into pi x f of n plus 1 xi dx. Note that xi is dependent on x, therefore, I cannot take f n plus 1 xi outside the integral and write it. It will be part of the integrand. Now, this integral is difficult for us to evaluate. Now, we will set it equal to summation k is equal to 0 to n some lambda k f of x k plus r n, where we have denoted this integral by lambda k and this error term as r n. Therefore, we can write lambda k is equal to a to b w x L k x dx and the error term r n is 1 upon n plus 1 factorial integral a to b pi x w x f n plus 1 of xi dx. As I mentioned earlier, it is difficult for us to evaluate this integral unless this part pi x into w x has got some special properties which we may not always have it. Therefore, I would like to write an alternative method for finding r n. So, let us call this as alternate method for finding Rn. We know that the formula is of order n. So, that is the first step that we shall note. Therefore, it integrates all polynomials of degree less than or equal to n. Integrates exactly all polynomials of degree less than or equal to n. That means, it integrates exactly 1 x, x squared and so on x to the power of n. This implies that if f x is equal to x to the power of n plus 1, then R n plus R n is not equal to 0. This error is not going to be equal to 0. Therefore, if R n is equal to 0, then it is going to integrate exactly polynomials of degree n plus 1 also. Hence, if we use x to the power of n plus 1, now if R n is equal to 0 for f x is equal to x n plus 1, then the formula is of order n plus 1. That means, hence we shall use f x is equal to x to the power of n plus 1 and determine the error constant in the error. We shall call the error constant as c, you can call it by any other name. Therefore, c is defined by integral a to b w x x to the power of n plus 1 dx minus summation k is 0 to n lambda k x k n plus 1. In the integration rule, f x is replaced by x to the power of n plus 1, f of x k is replaced by x k to the power of n plus 1. Then error is defined by R n is a c upon n plus 1 factorial f of n plus 1 of eta, where eta lies between a and b. So, let us take let w x is equal to 1, that is weight function is equal to 1. Then our lambda case would be simply integral a to b L k x dx. So, w x is equal to 1, it is simply the integral of the Lagrange fundamental polynomials, that is L k x, and let us open it up. Therefore, this is equal to integral of a is equal to x naught, b is equal to x n, x minus x naught, x minus x 1, x minus x k minus 1, x minus x k plus 1, x minus x n divided by x k minus x naught, x k minus x 1, x k minus x k minus 1, x k minus x k plus 1, x k minus x n dx. I have written the Lagrange fundamental polynomial with respect to the abscissa x k, because left hand side I have written lambda k, I will write corresponding to lambda k, if in the formula it is lambda k f x k. So, I have been writing lambda k with respect to the abscissa x k. Therefore, I will be missing the term in the numerator x minus x k, and this is the Lagrange fundamental polynomial. Now, I will assume that we are taking the equispace. Let us take the equispace abscissas. equispaced x, and let us define x minus x naught by h is equal to some s. Which is same as x is equal to x naught plus s h. Now, with respect to this particular substitution, I would like to derive what is the numerator and denominator. For example, x minus x I would be equal to x minus x naught plus I h, x I is equal to x naught plus I h, which is same as x minus x naught minus I h, but x minus x naught is s into h, that is equal to s into h minus I into h, that is s minus I into h. So, I can set I is equal to 0, 1, 2, 3 so on, and then I can obtain the expression for each one of these terms that we have over here. And similarly, if I take the denominator is x k minus some x I, x k minus x I, x k is fixed, x I is varying. Therefore, this I can write as x naught plus k h, and x I is equal to x naught plus I h. Therefore, this is k minus I into h. Therefore, we are able to get the expression for each one of these factors that we have here. So, let us now write down what is the denominator. Now, denominator, if I take this, first term is x k minus x naught. So, I is equal to 0. So, first term is k h. So, I will have here k h. The next term is x k minus x 1, I is 1, that is k minus 1 into h, k minus 1 into h, and so on. I have got here x k minus 1, therefore, k minus 1, therefore, I will have plus 1 into h. So, I will have a h here. Now, the next term is x k minus x k plus 1, therefore, I will have here minus k minus 1. So, I will have here minus h, and so on. The last term is n minus k into h. This is your n minus k with a negative sign. I have written n minus k. This is your k minus 1 into h. So, this is minus n minus 1 into k. Now, let us simplify this. The number of terms here are n, number of terms are n. Therefore, each one is giving us a h for us. So, it is giving h to the power of n. With the negative sign, there are n minus k terms. So, I will have minus 1 to the power of n minus k. And if you look at the first one, this is 1 into 2 into 3 into k. So, this will contribute factorial k. This is 1 into 2 into 3 n minus k. So, this will give you n minus k factorial. This will be the denominator, the simplified form of the denominator. Now, let us write down the numerator. Now, here we have x minus x naught, therefore, I have to substitute I is equal to 0 in this. Therefore, this is s into h, therefore, I will have s into h as the first term. Then I substitute I is equal to 1, so I will have s minus 1 into h. And I have to go up to x minus x k minus 1. So, we will have here x minus k plus 1 into h. Then we have x minus x k plus 1, therefore, I will have s minus k minus 1 into h, and so on, and the last term is x minus x n. So, I put I is equal to n. So, s minus 1 into h. So, we will have here is S minus n into h. Number of terms are n, therefore, I will have here h to the power of n again, and the remaining is s into s minus 1, s minus k plus 1, s minus k minus 1, s minus n. Now, I can substitute the denominator and the numerator in lambda k. So, if I do that, let us write down lambda k. Now, the when I substitute h to the power of n cancels with h to the power of n. So, we can drop off h to the power of n. Furthermore, we have dx here, and dx is equal to s times dh. We will have here is equal to h times ds. Therefore, dx is also contributing one h term. Therefore, I will have outside h here, these h to the power of n cancelled, this is minus 1 to the power of n minus k, I will retain it as it is. Denominator is factorial k, n minus k factorial. So, this is the term in the denominator, this is a negative sign whether you write numerator denominator it is same. So, I have written this term, and integral of the lower limit is x naught. When I substitute x naught here, s will be 0. When I put x is equal to x n, this is n h by h, that is n, therefore, s will be n. Therefore, the limits of integration are for s is equal to 0 to n, the limits for s are 0 to n, and the integrand is given by simply this quantity, that is s into s minus 1, so on, s minus k plus 1, s minus k minus 1, so on, s minus 1 ds. Now, we can also write down from here what will be the error term. The error term that we had written is this. So, I can write down the error term from this using this, let us write error, that is equal to R n. Now, the numerator w x is 1 we have taken, pi x contains all the products. All the products means it will now contain the missing factor also that we have missed here s minus k. So, that missing factor will come here, and hence it will be h to the power of n plus 1, and there is a h being contributed by dx. Therefore, we will have here h to the power of n plus 2, h to the power of n plus 1 contributed by this, and dx is equal to h times ds. Denominator is the same, that is your n plus 1. So, we will have n plus 1 factorial, integral of 0 to n, and s into s minus 1, all the terms are here. So, simply s minus 1 f n plus 1 of xi ds. This is the error term for the most general case, and these lambda k's are the weights in the integration formula, and this entire set of formulas are called Newton-Cotes formulas. They are called Newton-Cotes formulas. If I take particular values of number of points n, then I have various order formulas coming. Let us first of all take a case n is equal to 1, which is a 2-point formula. This will be a 2-point formula. Remember, we are taking n plus 1 as the total number of points. So, if I take n is equal to 1, we are taking 2-point formula, that is your x naught we are taking, f x naught we are taking, and x 1 f x 1. These are the 2 points that we are taking. Therefore, h will be simply equal to x 1 minus x naught, that is equal to simply b minus a. We are taking the entire interval a to b as only considering 2 points, therefore, it will be the upper limit and the lower limit, therefore, the distance between them will be your step length b minus a. The formula will be integral of a to b f x dx, w is equal to 1. So, f x dx is lambda 0 f of x 0 plus lambda 1 f of x 1. This is our formula, of which x 0 and x 1 are fixed as a and b. Now, lambda 0 I can obtain from here. Let us substitute k is equal to 0 in this to get our value. So, I have to put n is equal to 1, k is equal to 0. I have to put here and k is equal to 0 and n is equal to 1. Therefore, we will get lambda 0 is equal to n is 1, k is 0. So, I will have a minus sign, minus h, this is factorial 0, factorial 1. So, I will have denominator simply as 1, integral of 0 to 1, there only n is equal to 1, 0 to 1, and the numerator should not contain x minus sk term, that is your x minus x 0 term, that means I should not have s in the integrand. So, I will simply have s minus 1 ds. Since we have taken only n is equal to 1, we will have to consider only 2 terms of this. So, of this lambda 0 s will be missing, for lambda 1 s minus 1 will be missing. So, s is missing, so I will have simply this. Now, I can integrate this and write this minus h, s square by 2, that is half, minus s, that is 1. So, that is equal to h upon 2. Now, we have obtained already lambda naught. So, let us obtain lambda 1. So, now I have to take n is equal to 1, k is equal to 1. I have to take n is equal to 1, k is equal to 1. So, let us put in this n is equal to 1, k is equal to 1. Therefore, I will have lambda 1. Now, n is 1, k is 1. So, it will be positive sign, and this is 1 factorial, this is 0 factorial. So, again I will have 1, 0 to 1. Now, s minus 1 will be missing. So, I will simply have s ds. Therefore, this will give you h square by 2, that s square by 2, therefore, that is equal to 1 by 2. Therefore, we have now derived the formula as integral a to b f x dx is equal to h by 2 f of x naught plus f of x 1. If you want, we can put it in terms of the upper and lower limit also, h is equal to b minus a. So, I can alternatively write this as b minus a by 2 f x naught plus f of x 1, and again b minus a by 2 f of a plus f of b. So, I can use this particular form, or I can use this particular form for computation purposes. Now, let us write down the error term. The error term is given by this. Now, n is equal to 1, therefore, our error R n is h cubed by factorial 2. I am putting n is equal to 1 here, 0 to 1 s into s minus 1 f n plus 1 xi ds. Now, it is possible sometimes for us to use the mean value theorem of integral calculus to evaluate this, as we have done earlier also. You can see that this product, this function s, has got negative sign between 0 and 1. So, it has the same sign, minus sign in 0 1. Therefore, I can apply the mean value theorem, where when we have 0 to 1, some f x g x dx is there, f x does not change its sign, then g x can be taken out of the integral and evaluate it at any point in between 0 and 1. So, apply the mean value theorem, use mean value theorem of integral calculus. if I use this mean value theorem of integral calculus, I can now take out this fn plus 1 out and write this as h cubed by factorial 2 n is equal to 1 f double dashed of some eta, some other point, some point in this one, into integral 0 to 1, and let us multiply it out, s squared minus s ds, where eta is lying between a and b, eta is lying between a and b. Now let us evaluate this. This is equal to h cubed by 2 f double dash of eta, this is x cubed by 3, that is 1 by 3 minus 1 by 2. This gives you minus 1 by 6. So, minus h cubed by 12 f double dash eta. If I want in terms of b minus a, I can also write in terms of b minus a whole cubed by 12 f double dash of eta. Now n is equal to 1, therefore, as we have shown earlier, this integral formula integrates exactly polynomials of degree less than or equal to 1. Therefore, this integrates polynomials of degree less than or equal to 1, that is all linear polynomials it will integrate exactly. Therefore, integrates exactly polynomials of degree less than or equal to 1. That is because order is going to be n is equal to 1. Indeed, of course, we could have observed or derived this particular thing by looking at this error term. The error term consists of f double dash of eta. Now, if f is a linear polynomial, its second derivative is 0. Therefore, Rn is always going to be 0 whenever our fx is a linear polynomial. Therefore, the conclusion that we have given here could be obtained by, if you are able to derive the error formula, I can obtain the same observation from the error formula also. This formula is called the trapezoidal rule or trapezium rule. This is called the trapezium rule, trapezoidal, or we can call it as trapezium rule. If you are looking at integral a to b fx dx, why it is called a trapezium, I am just trying to explain. If you are taking, this is nothing but area under the curve from a to b fx. So, if I draw the graph of this, let us write a nice graph like this. Let us take this as a, let us take this as this b. Then this is the graph of y is equal to fx. This gives the area under the curve between the abscissa x is equal to a, x is equal to b, and bounded by y is equal to fx above the x axis. Here what we are doing here is, we have written the formula as simply minus a by 2 into f of a plus f of b. That means what we have really done here is, we have now taken this as the approximate area. We have taken this as the approximate area by using this particular formula. This is nothing but the area of trapezium. Now, if you look at this trapezium, this is nothing but the area of the trapezium. Therefore, it is called the trapezoidal rule or the trapezium rule. Now, but the order of the formula is only 1, therefore, it is very useful. At the same time, we would like to have better formulas. So, let us go for n is equal to 2, that is your 3-point formula. That means we are using the 3 abscissas x0, x1, x2. They are equidistant, therefore, we are taking a plus b by 2 and b. These are 3 equidistant formulas, therefore, we will have a plus b by 2 and b. Now, I will have to substitute in this expression that we have derived earlier for lambda k. For finding lambda 0, I will have to substitute n is equal to 2, k is equal to 0, integrate this, I will have then I will have 3 terms here, s into s minus 1 s minus 2, one of them will be dropped for finding lambda 0, that is s will be dropped. When I find s1 lambda 1 I will drop s minus 1, when I find lambda 2 I drop s minus 2. So, it is simply integration of this between the limits 0 to 2, I have to integrate between 0 to 2. Now, I will give the values for the lambdas, that is very simple straightforward to be can be obtained, that is h upon 3, lambda 1 is equal to 4 h by 3 and lambda 2 is equal to h by 3. H of course is the distance between x 1 and x 0 and this, therefore, your h is equal to x 1 minus x 0 or same as x 2 minus x 1, therefore, this will be b minus a by 2. This is a 3 point. So, it will be 2 intervals, because the 2 intervals we are taking, the 2 intervals are x 0 x 1 x 2, therefore, the step length that we will be having will b minus a by 2. So, that it is divided into 3 equidistant points. Therefore, the formula would be integral a to b f x dx is equal to h by 3 f of x 0 4 times f of x 1 plus f of x 2. If I write in terms of the end points, upper and lower limit, I can write down b minus a, this is 2, therefore, I have a 6 here, f of a 4 times f of a plus b by 2 plus f of b. Now, let us write down the error also from here, error formula can immediately be written down, but the error formula as given is difficult for me. So, what I would do is I will write the alternative form of the error that is given to us. We have written the error constant, we have defined the error constant, I would like to use this to derive the error formula for this formula. Now, n is equal to 2, therefore, it should integrate polynomials of degree less than or equal to 2. So, let us first say integrates polynomials of degree less than or equal to 2. Therefore, our array term should come from the next power of x, that is x cubed. This is n is equal to 2, therefore, I must use x to the power of n plus 1, that is 3, and that should give me the error constant. Therefore, let us write down the error constant. The error constant c would be equal to integral of a to b x cubed dx minus or lambda naught f x naught. We will write down this expression, but just write down the original formula. Now, let us put the value of this. This is equal to integral a to b. Let us integrate this x 4 by 4. So, I will have 1 by 4 b to the power of 4 minus a to the power of 4 minus this is b minus a by 6. I am writing from here, I am writing from this formula. This is your f of a. I will substitute for x in a moment, but let us just write down the formula. This is 4 times f of a plus b by 2 plus f of b. So, let us put the value of f is x cubed, therefore, this is 1 upon 4 b to the power of 4 minus a to the power of 4 b minus a by 6, f is x cubed, therefore, this is a cubed plus 4 upon 8 a plus b whole cubed plus b cubed. Now, I will leave this as a simple exercise for you to just open it up and show that it turns out to be 0. Just multiply it out, everything cancels, and we will have only b 4 minus a 4 here, and we will get this is equal to 0. Therefore, the error constant has turned out to be 0. before we have written this we said it integrates polynomials of degree less than or equal to 2, but now error constant has become 0. So, it is integrating x cubed also exactly. Therefore, this formula is integrating polynomials of degree less than or equal to 3 exactly. Therefore, we conclude from here immediately integrates polynomials of degree less than or equal to 3 exactly. It is not 2 but 3. Therefore, the order of this formula is now 3. Now, I want the constant c, therefore, I must go to the next term, that is I have to go to a to b x to the power of 4 dx, that is the next value of x, that is x to the power of 4 dx, minus b minus a by 6 f of a, that is a to the power of 4 upon 16 a plus b to the power of 4 plus b to the power of 4, f of a plus b by 2 and f of b. Now, I can integrate this will give you minus 1 upon 5 x to the power of 5 by 5, that is b 5 minus a 5 and this. Now, I will leave this also an exercise for you. It turns out to be very simple expression as b minus a to the power of 5 by 120. This combines with this and they would all become a perfect factor and it become b minus a to the power of 5 by 120. Therefore, our error is not R2 but R3, n is now instead of 2 it has become 3. So, R3 is equal to c upon, if we had written the previous one it would be factorial 3, now c was 0. So, I will have factorial 4 f fourth derivative eta. Now, this also would now tell us that is the fourth derivative occurring for f, therefore, it integrates exactly all polynomials of degree less than or equal to 3. Therefore, we are proving from here also that it is a order is 3. Now, I substitute this, therefore, I will have b minus a by 5 24 into 120 f 4 eta. Now, this form I can use. Alternatively, I would like to use the form of the step length h. The step length h for this was b minus a by 2. Therefore, I can use b minus a is 2h. Therefore, b minus a to the power of 5 will be 2 to the power of 5 32 h to the power of 5 by 24 into 120 f 4 eta. This is 2880 and 32 cancels off, it becomes 90. So, I will have here h 5 by 90 h 4 of eta. Now, this class of formulas are called the Simpson's integration formulas. These are the Simpson rules. Some books call it as 1/3 rule, but whenever we talk of Simpson's rule we always mean this particular rule only, and this is a formula which has got precision or order 3 and the error term is quite small, that is h to the power of 5 by 90 fourth derivative of it. When f x is a continuous function that is given to us, f 4 is bounded, therefore, the error is now really governed by this particular factor that we have over here, and we can see by improving by 1 point the order has jumped also, and also it has become very accurate it is going to be. Okay, we would stop at this.